Alright, next we're going to go through the squeeze theorem. So the squeeze theorem basically states if you have three functions, so if you have one function, let's call that g of x, is less than or equal to h of x, which is less than or equal to f of x. So you have to have this condition first, where this function here, h of x, is being squeezed in between g of x and f of x. Okay, kind of like the figure here. Okay, this h function, it's in between the g function and f function everywhere for its domain. Alright, and then the point here where it looks like it intersects, that point doesn't actually exist. It's an open circle there. Okay, so this states if the limit of g of x as x approaches c equals L, okay, some value L, and the limit of f of x as x approaches c equals L, okay, so basically this function here and this function here, when you're taking the limit of both of those as x approaches c, both of those are going towards L or equaling L. Then you can conclude that the middle function here, as the limit of h of x as x approaches c, will also equal L. Okay? So that's what the squeeze theorem states. We are going to use that theorem to prove this example here, which this is g of x, this is f of x, and this is h of x. Okay? So we're trying to prove when we take the limit of cosine of theta as theta goes to 0 equals 1, and the limit of 1 as theta goes to 0 equals 1, then the limit of sine over theta as theta goes to 0 also equals 1. Okay? So first of all, we need to come up with a relationship to show g of x is less than h of x, less than or equal to h of x, and h of x is less than or equal to f of x, where g of x is cosine of theta, h of x is sine theta over theta, and f of x is 1. So first of all, we need to come up with functions where these relate, and this condition is true. So let's look at the unit circle here. Okay, let's draw a triangle like this. And let's draw another little triangle in here. Okay, so first of all, let's look at this little red triangle. Where this is theta, this is 1, this is 1. The height here, I'll call this h sub 1. Okay, so we'll call this g of x. And let's find the area of this triangle. So the area of this triangle would be 1/2 the base. Well, the base is right here, which is 1, times the height. The height is right here. So if we look at this triangle, look at sine theta. Sine theta of this triangle would be h1, which is the opposite side, all over the hypotenuse, which is 1. So basically, the height here is equal to sine theta. So I'm going to write sine theta here. Okay, so we got the area of that triangle. Next, let's look at the area of this sector that I'm highlighting in blue here. Okay? So we'll call this h of x, and that should make sense that g of x is less than or equal to h of x. The area for a sector, okay, the area for a sector is 1/2 r squared theta. So for this one, it's going to be 1/2 r, the radius is 1, so 1 squared times theta. And that's going to be less than or equal to f of x. F of x, I'll make that this yellow triangle here. Okay. Call this h sub 2. So that's going to be less than or equal to 1/2 the base, which is 1, and the height, which is h2, h sub 2. See if we can figure out what h sub 2 would be. You think about tangent of theta, that's going to be equal to the opposite, which is h sub 2, all over the adjacent, which is 1. So h sub 2 is equal to tangent of theta. Okay? Alright, so now let's see if we can manipulate this to get it to look like this. Because if we can get it to look like this, then we can use our proof. So let's simplify this a little bit. Let's make this sine theta over 2 is less than or equal to theta over 2, which is less than or equal to tangent theta over 2, or sine theta over 2 cosine theta. Okay, so that's just using some identities, multiplying, simplifying this. Now, let's multiply through here by 2 over sine theta. Multiply all the way through here. This one would become 1. The 2's would cancel out here, so this is going to be theta over sine theta. And this last one here, the sine thetas are going to cancel out, the 2's are going to cancel out, so this would be 1 over cosine theta. So now this is starting to look like this. What we can do here, we can flip the numerator and the denominator for each of these. So this would be 1. This would be sine theta over theta. And this would be cosine theta. Now, if you flip all of those, you also have to flip the inequality signs. So now this is just like this, because I can write this as cosine theta is less than or equal to sine theta over theta, which is less than or equal to 1. Okay? Now, using this right here, the squeeze theorem, we know if the limit of cosine theta as theta goes to 0 equals 1, and the limit of 1 as theta goes to 0, that also equals 1, then by the squeeze theorem, the function that's squeezed between these two functions, when you take the limit of that function as theta goes to 0, that also must equal 1. So we did this whole proof to basically be able to use from now on, whenever you take the limit of sine x over x as x goes to 0, we can conclude that this is 1. This is not a proof that you'll have to continue to reproduce. You'll just need to memorize this. So if you see a problem like this, the limit of sine over x, where x could be anything, could be theta, could be y, as x goes to 0, that's going to be equal to 1. Make sure that it has all of these conditions, because we're going to do some other problems later where the limit of sine x over x as x goes to infinity, then our answer would be something different.